Okay, continuing the start to finish analysis of single subject results. Where we left off was we had just finished running the proc script, and so we have the end of the AFNI proc results over here. And I'll come back to this later, but I just want to note the last two bits that are on the terminal, in the terminal window, and also saved. Again, this is all saved in this output.proc.ft text file. But as long as it's on the terminal window, I'll note it here. Here's one of the SS review outputs, and this is the basic output that's all text. It mentions the subject ID, the AFNI version and package, time points removed, final voxel resolution, stats data set, motion limit, how many time points were above that, how many time points were censored, 6 time points censored, the fraction censored, and then some general stuff, temporal signal to noise, average within whatever mask we specified, autocorrelation function. This is how blurry it is. That's the fraction of the blur estimate that's Gaussian, and this is the Gaussian size, and this is the linear size. So that's one bit of information, and again, this text is also stored in its own file. But then the last bit of output is a suggestion to consider this command, consider running this command. And again, AFNI Open-B is going to open a web browser, and this is the HTML QC results, so the quality control for subject FT. And if we just run this, I'll grab this command and copy and paste it into maybe in the other window. Again, when we ran the proc script, we ran proc.ft. It generated, well, it got input data from the FT directory. It generated the FT.results directory. That's where it ran the analysis. And all the text from that proc script was saved to output.proc.ft. So FT.results is where all the results are stored. And you can see this is telling us to open a web browser to an index.html file underneath that FT.results tree. So I'm just going to run this just to briefly see that it produces what I might expect it to produce, and it opens up that web file, and there we go. There's some QC, and we'll look through this in a little more detail later on. I didn't really want to cover it now, but I just wanted to mention that it's here. And you see the last bit in there is exactly the same as this SS Review basic output up here. So we'll come back to that, but since those are the last two things on the screen, I just wanted to point them out. So now that we've generated the ft.results directory, let's look in there, and we'll have two terminal windows running, one to run commands in and one to probably look at the script. So I think I'll leave my right terminal to look at the script since it's on the right side. New windows are less apt to appear there. Of course, that puts the text in the middle instead of the text on the left, but we'll try it out. And in this directory, I'll run some commands. So in this directory, let's cd into the ft.results directory. So cd ft.tab if you want to. And of course, you always follow it up with ls. And this has a lot of files in there. This unflipped file, we'll have to work on getting the name a little shorter. Since it takes up more than 40 characters, it produces single column output. This is a long file too. Anyway, so here are all the files that are remaining after the analysis. The ones that are probably worth noting at first are the PB files, PB00 down through PB04, putting them all on one screen here. So these are the EPI datasets as they go through pre-processing. So processing block 0 for run 1, run 2, run 3, is the TCAT block. Run 1, run 2, run 3, TCAT. Processing block 1 is the T-shift block. Processing block 2 is volreg, 3 is blur, 4 is scale. And after the scaling operation, this is the data that's ready for input to the linear regression. So that's the last output as a pre-processing step. So now let's actually look at the proc script and start reviewing the data as it's processed. So again, the proc script is proc.FT. You can maybe, if you're unsure of what editor or however you want to view it, you could use AFNI Open-E. Again, that's going to find some editor on your computer. I won't do it this way because I don't prefer this font or the colors. So I'm just going to open this with, I guess I'll use less. I'm not sure I want to use less either, but it's something everyone can run if you want to. And again, Q to quit. So looking at this, actually I'm going to sneak and run VI. Then I can get a nicer coloration. But you don't have to run VI. Preferably just use less or use AFNI Open-E. So this is a T-shell script. It's 512 lines long. There's some basic setup at the top. For one, it tells you the version of AFNI proc that was used to generate it. It tells you how to run the script. Remember, we saw that this is the output at the end of running AFNI proc to generate the script. So how to execute the script is also saved in here. And then we start having processing blocks. The first one is this setup block. We note the AFNI version, so you'll get that in the output file. For example, if I do less on output.proc.FT, whoops, it's up one. That's up one directory, so I'll just run less on that. One of the first things it does is executes AFNI-ver. So the version I'm running, it's Fedora 30 shared. Well, I guess I built that myself, but from April 14th, 2020. So that's the AFNI version. So this is the AFNI version I might end up, if I publish these results, I might use this AFNI version in the paper. Anyway, so this is all the text output from running the script. Checks the AFNI history. It's possible some people run AFNI proc to generate the proc script on one machine and then execute it on another. That does happen. And so AFNI proc just checks the history if the version that if the AFNI version on the machine that you're running the proc script is too old compared to the one you used to generate the proc script, it'll whine about it. So then it does some more setup stuff. It sets a subject variable, so our subject is FT, so the variable subj, such as right here, will stand for FT throughout the rest of the script. So the output directory where we store all the results is FT.results. If that directory exists, we whine about it and quit and go home in a snit. Otherwise, we continue on. We set runs as an array equal to or as a list to the output of this count command. And all this count command does, you notice the back quotes here that, again, I don't know if it's again for this particular set of videos, but whatever. The back quotes means run the command that's contained within them and put the output back on this command line. So if I grab that count command, I'll quit out of less. If I just grab that count command here, it just outputs dash digits to the numbers from 1 to 3. So 0, 1, 2, and 3. So it's as if this we're reading set runs equal parenthesis 0, 1, 0, 2, 0, 3 end parenthesis. So now runs is this list of 3, and later on we'll do some things for each run, just like here. So now we create the output directory, that's the ft.results directory, and we start copying the input data into it. So we create a stimuli directory and then copy the stimulus timing files into it. Then we use 3D copy to copy the anatomy, the FT and AT dataset, the T1 dataset into the results directory. And then we have another block, auto block, an automatic processing block. This one's TCAT. So in this block, we actually copy the EPI data into the results directory, but we also remove any pre-steady state volumes or whatever volumes the AFNI proc was asked to remove. So we asked to remove the first two from the beginning of each run. And so we have 3D TCAT -prefixes saying what's the prefix for the output, what should the output name be called, and it's going to be FT.results / PB00 subject ID run 1, 2, and 3.tcat. So in our results directory, that's what we see right here. PB00 is the TCAT processing block, run 1, 2, and 3.tcat, and we have brick and head files for each of the data sets. So that's what this command creates. Notice the input to that is again under the FT directory, FT API run 1 plus orig, for example, and then we have this AFNI syntax that says we want to grab only time volumes or only volume indices from 2 until the end. $$. Dollar means the last index. This is AFNI syntax. However, the shell cares about this. The shell uses this left square bracket for wildcard matching, and the $sign it uses for variables. We don't want the shell to interpret those characters. We want to pass those characters along with the input dataset name to the AFNI program, 3D TCAT, so that 3D TCAT knows we want to go from index 2 to the end. So that's why we have quotes running amok all over the script, in that we're hiding the special characters from the shell so that the shell does not interpret them, and it just passes bracket $2 end bracket to 3D TCAT. So now we're copying volumes from 2 to the end, skipping 0 and 1. The indices are 0 based, so we skip the first two volumes, and we use 3D TCAT to copy those volumes to the results directory. The data is not altered, it's just we're dropping the first two volumes of each run. So you can call this the original data after pre-steady state. And once we do that, we make a note of how many time points we have in each of the 3 runs. So there are 150 remaining volumes in each run. And now we've finished copying all the data to the results directory, all the input data, so we cd to the results directory and get to work. Now if you recall the AFNI proc command, S05, I'll just cat that. In our AFNI proc command, after the blocks option, we said we had that one of those QC options, radial correlate blocks. So we wanted the proc script to run radial correlate after the TCAT block and after the volreg block. So the last thing we do, so here's the next block, but above that we're the TCAT block. So at the end of the TCAT block, the last thing we do is run at radial correlate. That's doing that voxelwise correlation. And I'll try to remember to look at that later. I don't want to look at it right now because I want to get the AFNI windows set up. Well, that's okay. Let's just run AFNI for an initial setup across the top of the screen here, and then we can verify the TCAT output, and then we can briefly look at the radial correlate output. So the left window is where I'll run the commands, and I'm sitting in the FT.results directory, just as present working directory shows. There are all my files, and I'll run AFNI here. And for the most part, I think I will focus on, I'll use Q to close a couple of the windows. I will focus on the axial window and basically just have one set of control windows up at the top half of my screen, and then I'll have it later on. I'll put some stuff on the bottom half. So let's just look at one of these resulting data sets for the moment, and we'll start with PB00 for run 1. So let's, in the AFNI controller, let's hit the black underlay button, and we'll select that first PB data set, processing block 0.run1.tcat. And you can hit set or apply. Again, apply means you make the selection, so I've already jumped to my TCAT dataset. It says if I hit apply. But apply leaves this window here. If I hit set, it's just like apply, but then it subsequently closes the window. So fantastic. And I'll open a graph window as well. Here's a graph window, and I'll make that a little smaller. Hopefully this might get a little tight here. I've lowered the resolution of my recording. I may pay the price for that. We'll see. Anyway, now let's go find some time series that looks reasonable, and then we can use that for navigation to keep us all in the same place. So we're seeing some good voxels down here. Maybe I'll go a little more superior. This is a lot of nice stuff here. Okay, well that's great. That's good enough. So now let's get everyone to this location. I like doing this a little randomly just so we get used to hopping about, because you should practice perusing your data. Don't just assume to look at it in one way all the time. You should, hop around a little bit. So to get to this location, you can either jump to the IJK indices here, 48, 74, 11, or you can jump to the coordinates. And let's jump to the coordinates. So you see the coordinate order is an RAI order, so right to left, anterior to posterior, inferior to superior are the coordinates, and then R and A and I are the negatives. So left is positive, post P is positive, S is positive. But so let's all jump to this location. So in the image window, I'll right click and jump to XYZ. And now we can specify these coordinates. And we only need to be approximate. Whatever we put in here, it will jump to the voxel center that's closest to the coordinates we type in. These are the voxel center coordinates of the one in the middle of the green box here on slice 11. Notice this 11 matches this 11. But we'll give coordinates instead of indices. So we can just type in like 19, 81, 15. So we'll jump to XYZ 19, 81, 15. And I'll hit apply, or I guess I'll hit set. We don't need the window. And did I just move? Jump to XYZ, set. So now we should all be looking at the same thing. In theory, I shouldn't have jumped anywhere because I was already there, but I think I accidentally clicked in the image window or something. So now we're all looking at the same time series, and what you notice, actually, we've got the coordinates saved so we can jump around. One thing you notice compared to the original input data is we don't have the pre-steady state volumes anymore, right? There's no initial transient. There's no spike at the beginning of the runs. That's because the proc script removed the first two time points. Fantastic. But of course that motion spike is still in there. In some places you see it, in some places you don't. Here it's enormous. And the places where it'll be the biggest are when you jump between tissue types. If the motion takes you from one tissue type to another, you'll have a big signal change, or percent signal change, say. If you're within a tissue class, like gray to gray, or white to white, or CSF to CSF, there might not be a big change. Like in this voxel, we're probably in the middle of white matter here. Not a big spike. Anyway, let's go back to our voxel of interest. I'll right click again and jump to XYZ. It still has the coordinates saved. Fantastic. So you notice that even at this current voxel, I see the apparently enormous signal change here, but there isn't even any major motion spike. So we're probably fairly in the middle of the gray matter here, at least relative to how the motion occurred. But up here, even one voxel that's from here going that direction, this 3x3 grid matches the 3x3 grid in that box. Just briefly, I'll hit some capital M's for the matrix size, M, and make it bigger, or make it contain more voxels. And what you notice there, I'll hit plus as well to make it taller. This box is getting big, so now we've got 7x7 here, 7 voxels by 7 voxels, so our green box is a 7x7 box. And so just to reinforce the fact that this grid is matching, it's an axial graph window, so the voxels in this grid match the voxels in the axial image according, within this green box here. So let's go back to hit some lowercase m's, go back to a 3x3, make sure I'm in the correct location, and I'll hit a lowercase a just to do automatic scaling. Okay, wonderful. So you notice again, since we're in an axial image, the point was going from the bottom to the top of this graph window is like going from the bottom to the top here, which is going from posterior to anterior. So when the voxel is a little more anterior than the central one, we do have a big spike. But at this level, we don't. Okay, so now that we've looked at that, let's just take a moment and we can peek at that radial correlate result. So if you look at the files in the current directory, I'll go back to my AFNI window. If I list them in chronological order, ls-ltr, I'll make this a bit wider briefly. Let's find the PB00 datasets. So here they are. So of course they're copied before we do any other processing. So we made the PB00 datasets, and then what was created at approximately the same time, or oops, that's PB01. Okay, but I can't tell the difference between 0 and 1. So here's the PB00 dataset, and right after we created that, we have this radcor directory. So this directory has the output from running at radial correlate. So this has an option RDIR, that's short for results directory, radcor.pb00.tcat. So that's the name of the directory where it puts the results. Just for quick kicks, I will run AFNI on radcor pb00, or let's just type ls on that. And you see in that directory it has an underlay for run 1, 2, and 3, and then radcor correlation datasets. So if I'll leave the initial AFNI running there, and I'll just run AFNI on radcor.pb, not valreg, but the pb00.tcat one. And so here's just a single EPI volume for an underlay, and I'll set my overlay to be one of the radcor blocks. So I'll just pick the first one from run 1. And what this does, well, let's do some thresholding first, and then we'll talk more about it. You can see the outline of the brain here, though, right away. If I drag up the threshold a bit, 0.8 becomes immediately too high. And you see that we probably don't want to use the scaling of 10 to the first. That goes from 0 up to 10 to the first. Let's change it to go from 0 to 10 to the 0, so that's a 0 to 1 range, and that's more reasonable since what we're looking at are correlations. Now if we drag the threshold up, it's a little more usable. We don't have to be so precise. Wonderful. So what these are, the values are correlations, and at each voxel we're basically computing a Gaussian blur and getting some sort of Gaussian weighted average. So at this voxel, say I'll just jump somewhere. Let me get off the midline. So at this voxel here, we compute some Gaussian weighted average around it with like a radius of 20 millimeters or so. That's like a full width at half max of 40 millimeters. Full width is more of a diameter, but it's more natural for us to ponder in terms of a radius. So it's a 20 millimeter half max radius Gaussian weighted spherical average that we're correlating against. So it's okay to see structural correlations. You expect this to be correlated with a voxel to be correlated with its neighbors, but you don't want to see like big blobs that are certainly non-structural. Would be bad. So you see a lot of motion correlations here, like up here, this has got to be a motion correlation pattern. We can't really look at a graph. We only get one value again because our underlay is just a single EPI volume. But anyway, there you go. So these are the purpose of this is just to see if there's anything strange. Having motion in the data set, remember this data has not been motion registered yet, but we can see that there's nothing too strange here. If we jump around a little bit, it looks like mostly motion and perhaps some bold correlation. Who knows? We'll worry about that later. Okay, so I'll close AFNI. So what I just closed is the AFNI running in the radcor directory. I'll just Control-C to not re-execute that command, and we'll continue on with the script. So that finishes up the TCAT block, and maybe I'll just pause the video here or stop the video here, and we can continue with a new one in a moment.